So before we begin with everything, let's talk about what is power factor. So power factor is active power, also referred to as kW, over apparent power, which is also referred to as kVA. And this would give you the power factor, which is also referred to as PF. So what is kW? kW, or active power, is the power that actually performs useful work. kVR is reactive power, which is necessary. Yeah, let's talk about components of power factor. So we have kW, kVAR, and kVA. So kW is the power that actually performs work. Okay, so kVAR is required to maintain voltage and deliver active power as it converts the flow of electrons into useful work. And kVAR is the apparent power, and it's kVAR plus kW. Okay, so let's look at a real life example. So suppose you go to the store and buy a bag of chips. Let's say it's, I don't know, Lay's. So you're buying this pack of chips and it contains both air and chips. So here in this example, we can look at the air as being kVAR, or reactive power, and the chips being the kW, or the real power. And both of them together would give you the kVA, or apparent power. Another example could be the light bulb. So for the light bulb, the kVAR would be the light it produces, and then the kVA is the heat produced. Okay, let's go into more detail. Suppose you have a motor. This motor is rated at 100 kilowatts with a power factor of 0.85. So looking at this, we can draw this triangle. So since we have 100 kilowatts and a power factor of 0.85, this would give us 100 kilowatts divided by 0.85 equals 118 kVA. Okay, so next let's talk about bad power factors. So what does it mean to be a bad power factor? So it means that more money is spent on the electricity, and there's an increase in load for the electricity, and it's really inefficient. And this is why people say that a good power factor is necessary. How do you fix a power factor though? So in order to fix a power factor, you can add capacitors, and this would help reduce the reactive power. And overall improve the power factor. So what causes a bad power factor? So usually these would be caused by transformers, inductors, motors, amongst others. Okay, so first things first, we need to connect the FGAN to the positive. Then we need to take the ground and connect it to the negative. And then from the positive, we place our 1K resistor and just place it anywhere. And then from that 1K, in series, we place our 220 ohm resistor. And then we have our 100 millihenry inductor, which is going to be placed from the ground and in series with the 220 resistor. Next, we're going to connect this 1 microfarad capacitor in parallel with the inductor and the 220 resistor in order to see a difference between having the capacitor there and without it. Okay, so now for the FGAN. So how would we connect the oscilloscope? So the positive for the first channel would be connected to node B, and with the negative of the first channel being connected to the ground. As for the second channel, we're going to have the positive connected to node A over here, and the negative being connected to node B.
Okay, next we move to the calculation of the power factor. First, you need to find the phase difference. The phase difference you get from the graph that taken from the oscilloscope, and we have this equation, the dt value that was on the graph, and then division times the time per division and multiply by the full angle of 360 degree. So on the graph that we have, we can see that the dt value is 340 microsecond, and then we divide it by the division is approximately 3.3, and the time per division we set on the oscilloscope is 5 milliseconds, and then we multiply by 360. And the division we get is from the boxes. As you can see from the graph, it approximately 3.3 from peak to peak, and then as the result we get minus 7.42, and then this is only at R node, and then we'll calculate the second one is the RL node, which will have the same value but in the positive. In R node, it has minus because it's lagging, and the RL node positive because it's leading. And then next, we calculate the VRMS value. The V peak we get from the graph, it's 3.49 divided by square root of 2, and then we get the result as 2.469 volt. And then next, we calculate the power factor, which has the equation of cosine of the angle. Cosine of 742, it's equal to 0.992. In this power factor, the minus and the plus sign doesn't concern here. And next we move to the real power. It has the equation of VRMS times IRMS times cosine of the phase difference. it's equal to the RMS that we get is 2.4096 times the RMS we get from the measurement, the manual measurement, it's 3.65 milliampere, and then we multiply by the cosine of minus 7.42, and as the result we get, okay, from the real power, we have the equation VRMS times IRMS times cosine. It has two different nodes, and then we calculate first on the RL node. As you can see, we have the VRMS is equal to 2.4096 times of the RMS is 3.65 milliampere, and then we multiply by cosine of 7.42, and as the result we get 8.93 times 10 to the power minus 3, and then we move to the second node at R. It has same equation, but only the difference is in cos, because in R node there's no inductance, means there's no phase difference, and we put the cos is 0, so the cos 0 equal to 1, so we get this value 9.011 times 10 to the power factor of minus 3 watt. And for the real power total value is, we add these two values and then we get 17.941 watt, something like that. And then for the reactive power we have the same equation, but in reactive power we use sine instead of cosine, so we get of 2.496 times 3.65 milliampere, and then times sine of 1.129, and the result we get is 2.02 times 10 to the power factor of minus 5 VAR. And then for the last one, we want to calculate the apparent power, is the real power, which is 17.941 times 10 to the power factor of minus 3, and we divide it by the power factor, or the cos sine of angle is 0.9092, and then we get the result is 0.018 VA.